So it's good morning, afternoon, or evening to everyone. And on behalf of EuCAPT, I would like to welcome all of you today to the EuCAPT colloquium, the third EuCAPT colloquium this year. And we are all very pleased that you can join us today. It's my pleasure to introduce our speaker, Denise Boncioli. She's an associate professor at the University of L'Aquila. Denise completed her PhD at the University of Roma Tor Vergata, working under the supervision of Giorgio Mattiè and Sergio Petrera. She then held a postdoctoral position at Desi Zeuthen in the Walter Winter Group, and later continued her research as a senior postdoc at GSSI in L'Aquila. Over this year, Denise has become an expert in cosmic rays at the highest energies, with a particular focus on cosmic ray propagation in the universe and the associated multi-messenger signature. Her work spans from the physics of secondary diffuse emission, cosmogenic neutrinos, neutrino sources, and recently also Lorentz invariance violation, addressing some of these key questions about how ultra-energy particles are produced in the universe and then how they travel across cosmic distances. Among her major achievements, I would like especially to highlight that since 2024, she has been serving as one of the two scientific coordinators of the Pierre Auger Observatory, which is a vast experiment dedicated to exploring ultra-energy cosmic ray particles using both charged and neutral messengers. And this explains why we decided to invite Denise today to present on this specific topic, which is tracing high energy interaction in the universe with neutrinos. And please, everyone, join me in welcoming Denise. And thanks, Denise, for having accepted our invitation.
So thank you very much, Carmelo, for the introduction, and to all of you organizers for inviting me. So I guess I can start. I don't know if I have to wait a few minutes more for.
I think you can start.
So thanks a lot again. So I'm going to talk about today about the high energy neutrinos and how measuring and modeling the candidate sources might help us in tracing where the high energy interactions happen in the universe. So let me see, okay. So this is the outline of the talk. I'm going to give a large introduction about, with some words about how high energy neutrinos are detected, and then about the state of the art of the measurements and upper limits. So in this, I will.
Sorry, Denise. I get from the chat that the audio is not very well. So can do you have a mic?
It is the same as we tried before. So. It's weird that doesn't. I don't know if it helps now.
Maybe if you get closer a bit, yes. Thank you.
Just try to. So now it is a little bit closer. I hope it helps.
Yes.
Okay, so yeah, I'm going to talk about, especially in the list of the measurements that we got recently, especially from IceCube, about the high energy neutrino events and the association with astrophysical sources, as well as what we can get from multi-messenger connections. So I will be talking especially about in the case of the association of high energy neutrinos and their sources, about the possible candidate sources, but in particular also about the possible production site within the sources. While then I will talk about the connection between high energy neutrinos and the characteristics of ultra energy cosmic rays, in particular what one can get from the measurements, if any, of ultra high energy neutrinos, about the redshift evolution of the distribution of sources and the proton fraction in ultra energy cosmic rays. So just to give an overview of the neutrino energy spectrum, what we are going to focus on today, it is the extremely high energy part, meaning basically that part in which we see in this spectrum that we have data from IceCube. So the energy region, which is basically at the very end of the contribution of the atmospheric neutrinos, which are those ones that are created in the interaction of the cosmic rays with the atmosphere. And then in 2013, we had the discovery of IceCube of extraterrestrial neutrinos. Then in the very end of the energy spectrum, we expect to see neutrinos which should be produced in the propagation of cosmic rays in the extragalactic space, which are called cosmogenic. And so in particular, one could name the flux, the parts of the flux of the neutrinos as astrophysical, as those ones which are produced by interactions of cosmic rays in the astrophysical sources, which could be those ones which basically give the most of the IceCube spectrum, while cosmogenic neutrinos are those ones which are produced on the way from the sources to the detection. How high energy neutrinos are produced? So this is connected to cosmic ray protons or other nuclei in interactions which can be photohadronic or hadronic in the production of the delta resonance that then decays and produces mesons. And in the decay of those mesons, we have in the end, we can have gamma rays from the decay of the neutral mesons, and then we can have neutrinos in the decay of the charged ones. In this decay chain, the mesons can carry more or less 20% of the energy of the primary proton, of the nucleon in the nucleus, and then the final neutrino can carry about 5% of the energy of the primary proton. So these messengers are strongly connected to each other. So just a few words about how high energy neutrinos are detected, just a few examples. There are many more than what I'm showing here, because then I want to focus on the measurements themselves and on some interpretation. So first of all, I just want to spend a few words about IceCube, which is the neutrino observatory, which is located at the South Pole, which is composed by a surface array on top of the ice, and then in ice detectors, which are more than 5,000 optical modules, which can measure the Cherenkov light, which is emitted by the particles which pass through the ice. On the right, you can see actually which neutrinos can be detected by IceCube, namely those ones which come from the atmospheric part on top of the detector, but also those ones which can pass through the Earth. And then also a timeline of the main discoveries of IceCube and from the very beginning of its construction. Then I will be talking about some of these recent findings. And then in the ice, in this facility, what one can do is to measure a track. So what is produced basically by muons, which pass through the detector, and then they come from charged current interaction of muon neutrinos, which have interacted somewhere outside of the detector. This is very good for angular resolution, so for the reconstruction of the direction where the neutrino comes from, which is, of course, very relevant to then try to find some association with the sources. And then there is also the possibility to see the showers. So when basically the energy which is deposited is entirely contained within the detector, and this is produced by charged or neutral current interactions, and this is very good for the energy resolution. Other possibilities to look for neutrinos are, for instance, what is done at the Pierre-Auger Observatory, which is actually conceived for the measurement of ultra-energy cosmic ray particles, but actually it is also possible to look for showers which are initiated by neutrinos. So in this case, the Pierre Observatory, it is measuring cosmic rays in an indirect way, so through the particles which which compose the cascade, which has been initiated by the first cosmic ray which arrive in the atmosphere. So the neutrinos can be searched for with showers initiated with neutral or charged current, or also with showers initiated not just in the atmosphere, but also in the Earth by tau neutrinos, which undergo charged current interactions and produce a tau, which leaves the Earth and then decays in the atmosphere. Of course, there is a huge background of showers which are initiated by ultra-energy cosmic rays. And then what is done and what is depicted in this bottom plots is to look for inclined showers. So in those showers, basically, in general, the electromagnetic component is the one which is decreasing much more than the muon component. And this depletion increases with the inclination of the shower. So basically, since the neutrino is much more penetrating than a cosmic ray, then if we see a shower in which there is still some electromagnetic component, this can tell us if this is a shower initiated by a neutrino. And this is done mostly, this is done with the surface detectors, which are in this array, which is reported here. So, as for the state of the art of the measurements, the main points in this case are the measurement of the astrophysical neutrino flux, which is reported by EuCAPT, and the recent finding of a break in the spectrum. So the black data points are those measured by EuCAPT, and the red band is the broken power law, with which they can fit the data. And then there is a hardening below 30 dB. And then on the other side, the lines which report on the upper limits at energies which are above 10 to the 16 or 10 to the 17 eV, and which are the most sensitive ones being the light blue one, which is the one by EuCAPT, and the green one, which is the one by Auger. The dashed lines are reported as for the observatories or the facilities which are going to be upgraded or which are going to be constructed in the future. As for now, the highest energy neutrino ever detected has been announced almost 1 year ago by KM3net, which is instead an observatory which is located under the Mediterranean Sea. And the estimated energy of this neutrino is more than 200 dB. The gray cross is the flux that has been reported by KM3net related to this measurement, while then taking into account also the null observation by EuCAPT and Auger, this tension with the upper limits, which are actually here for EuCAPT and Auger, has been now, it is a little bit less, so at the level of 2.9 sigma. So after this announcement, of course, there were many papers, both from KM3net and from many other authors in literature for investigations about the origin. But what I want to talk about then in the following is what do we learn actually about astrophysical scenarios from ultra-energy neutrino events, or even from the absence of those events. Then another very important result which comes from EuCAPT is the detection of neutrinos from the Milky Way, so which is again also in this case neutrinos which have been produced by the decay chain of pions, which have been produced themselves by the interaction of protons with the matter in the galaxy. Actually, then what I want to focus about is at the extremely high energies, and in this case I'm interested in discussing what are the possible directions to which the neutrinos point, because this is how with neutrinos, which are neutral, we can point to possible candidate sources. So there have been a huge amount of effort of searching for correlation of neutrino events with the catalogs or with sources in general, with different techniques. So there have, like what I'm showing in the top plot, this is the search which has been done after the detection of the neutrino in coincidence with the TXS, about which I will be talking about later. And then there are searches for correlation with different known high-energy gamma ray sources, as well as any kind of possible sources such as blazars, gamma radio bursts, fast radio bursts, tidal disruption events. So both for correlations in directional correlations and in time domain. There have been also searches for coincidence with other messengers, such as gravitational waves and cosmic rays, which have been giving not positive results. So then just to summarize this, because there have been, as I said, many efforts, a wide range of candidate sources have been investigated, and stacking analysis can reveal what is the relative contribution to the diffuse flux. So in this plot on the right, it is nicely reported what are the relative contributions of different source classes to the total neutrino flux, which is measured by IceCube. What is interesting to notice is that the active galaxies, which are reported here on the right, or I mean, in general, what we can get from this collection of analysis is that we do not have strong evidence of gamma ray emitting populations as main contributors to the neutrino flux, and this was also a result which was reported by IceCube already in 2017, that the blazars contribute to less than 17% of the diffuse flux. And this actually reminds us of the connection that we would expect naturally between gamma ray sources and neutrinos. So actually this connection, which is natural, and one could think very simply about what we find in the Watson and Bahal argument in P gamma and gamma gamma, in the energy which should go into neutrinos and photons. Actually, taking into account these basic arguments, one can see that the high P gamma efficiency, which is suggested by the IceCube data and the upper limits on cosmic ray luminosity densities, suggest actually that the direct gamma ray emission from the sources, either it is leptonic or hadronic, is suppressed. And this is summarized in this paper from 2016, where they basically show what is the optical depth of gamma gamma compared to P gamma in the same sources. So it could be that the sources of neutrinos are actually hidden instead in gamma rays, which of course makes the scenario a bit more complicated than what was thought at the beginning. And then I want to highlight what are the indications that we have from multi-messenger alerts. As I started saying before, the detection of a single high-energy neutrino is promptly communicated to the astronomical community, so that targeted observations can be collected to identify, for instance, an electromagnetic counterpart. And this was what was done in 2017 when the IceCube Observatory announced the measurement of a neutrino in directional coincidence with a blazar in bright gamma ray state, which was a TXS 0506. And similarly, in 2022, the IceCube Observatory published an archival search for neutrinos, finding 79 events associated to this Seyfert galaxy, NGC 1068, which is reported here in this blue butterfly. There are also other indications which point to the possibility that neutrinos, for instance, could be produced in tidal disruption events, and this was reported in some papers, both from IceCube and other authors. And with this, and this I will discuss later, I want to introduce the other topic of my discussion, which is connected to the association of high energy neutrinos and electromagnetic signal and what we can learn from this. So then, based on what I have been reporting about recent observations, I want to discuss what I was just saying now. So what do we learn from the recent associations between astrophysical sources and neutrino events? And not just on this, because we are already at the level with the modeling to understand not just what could be the type of source, but also the production side in the source itself. And then in the second part, I want to show what we can learn from ultra-high energy events or from the absence of their observations in terms of the characteristics of ultra-energy cosmic rays and their source distribution, which can be done with a real multi-messenger approach. Okay, so then I want to go into this first topic about the association of high energy neutrinos and their sources, and then the site of production within the source. So first I want to briefly introduce what can be one of the main candidate sources for high energy neutrinos, which are active galactic nuclei, that are galaxies that present a compact and extremely luminous central region and broadband emission from radio to TV and sometimes variability. So on the right, you can see the spectral energy density of a blazar, Mercarian 421, from a multi-wavelength campaign. So this is just as an example to show what, briefly, what can be a source like this, which is powered by the gravitational energy released in the accretion process around a supermassive black hole at the center of the galaxy. And then there is an accretion disk, and then even a torus, a dust torus. Then there can be jets which are formed parallel to the spin axis, and as well powered by the gravitational energy released in the accretion disk, which is here next to the center. The classification actually of the AGNs is based on the viewing angle, depending then also on the intensity of the components of the spectrum. So there can be differences because of this intensity. So then I want to say something about this measurement of IceCube of 79 neutrino events associated to this NGC 1068, which is classified as a CIFER2 AGN. So if we come back for a second to this classification, this is an AGN which is for which we do not see the jet. So another thing to say is that, of course, neutrino observations cannot distinguish the emission zone. So if we look at this plot in which we see let's say the location of the neutrino event from where the neutrino event should come, which is the white cross, then we have the location of the spiral galaxy in the red dot. Then what we see in this plot is that corresponding to the IceCube measurement, the gamma ray flux is actually here. It is just this green arrows and dots. So what is supposed to power then the IceCube neutrinos, it is not coming in connection with gamma rays. And a possible explanation might be that of the X-ray emission, which is associated actually to the corona, which is in this sketch, this yellow ellipse. So in this region, very hot electrons, which are 10 to the 9 Kelvin, might do inverse Compton and then on ultraviolet photons from the accretion disk and then producing X-ray photons. So this is, connected to the position then of the photon field, which should be responsible of those emissions. Then I just want to clarify, or I mean to stress again, the energy region from which the neutrinos could come in connection with the position with respect to the central black hole. So with this dark green arrow, I marked, the direction of the arrow marks the distance, let's say, from the black hole. So I'm reporting here the corona, then the disk, and then the torus going from left to right. While the energy range of the photon field, even intuitively, could be thought as decreasing in this direction. So the more distant from the location of the black hole, the colder is the photon field, which means that the energy range of the corresponding neutrino flux is instead increasing with the distance from the center of the AGN. And this is what is reported, for instance, in these papers, just taken as examples, in which what is basically important, it is the connection between the energy of the photon, which is this epsilon, and the energy of the, and the Lorentz factor of the proton, which has been producing the neutrinos. So this multiplication has to match the energy of the photon in the proton rest frame, which is responsible then for producing the pion, and then for after that, from the decay of the pion, the neutrino. So from this, we understand, of course, that if we increase the energy of the photon field, meaning if we are closer, let's say, to the black hole, then we might have smaller energies for protons to produce those neutrinos. And this is what is depicted in these three examples, in which if we look at the peak, we see the peak increasing corresponding to these three different zones of the AGN. However, so this is just one of the necessary conditions to produce neutrinos, because we also have to account for the energetics. So how much energy actually goes into the cosmic rays to produce those neutrinos. And in this, I just want to give this nice example of the modeling that has been done after the measurement of the neutrino in connection with the TXS. So what you see on the left, it is a leptohadronic model, which has been studied, which has been reported for the interpretation, the joint interpretation of the SED of the TXS and the production of the neutrino. So in this case, basically, the bulk of the photon emission is of leptonic origin, but then there are also hadronic contributions, otherwise we would not have the neutrino, and they are as strong as permitted by the X-ray data. However, in some of these leptohadronic models, the required energy for the jet can be super Eddington. So there are more advanced models which can solve even this energetic, let's say, issue, in which the single zone approach is expanded and an extended jet is implemented where these physical parameters can vary, and then the jet power is kept as limited to sub-Eddington levels. So in this way, at least for instance, in this paper, this publication, there is a possibility to still to power or to reproduce the SED, and as well as to power the neutrino, which has been actually measured. Then I want to I want just to mention briefly, since I've been reporting that before, that there is also the possibility of other sources. I just picked these two ones, AGNs and tidal disruption events, as representative, but just for the discussion, so I'm not stressing too much about that. I just want to show that, for instance, at least in this case, there is the possibility that stars are torn apart by a supermassive black hole, and that the part of the debris is accreted and the jet can form. So these sources have been extensively studied as possible sources of high energy neutrinos, and then there can be acceleration in the jet, so that and presence also of hadronic particles, which then can produce neutrinos. This is just to say just a few words about the possibility that in one of the cases in which there has been some observation of association of neutrino emission to one of these events, that actually the neutrino event in terms of time does not happen in coincidence with the highest emission from the optical counterpart, but it happens a little bit later. So that means that the target for the proton interaction is not what one would expect, and even in this case there can be studies which include modeling as a function of the time of the photon fields which are present within the source, and matter field, of course. And then what one can do is computing the interaction time for different photon fields like optical to UV and X-rays, and do this as a function of the time, and then compute what is the amount of neutrinos, what is the fluence of neutrinos which is in connection with these different photon fields, and then realize what is the origin in terms of the target region of the neutrinos. So after this collection of ideas, or collection of results on modeling of sources, I want to pass to the part related to the ultra-high energy neutrinos and the characteristics of ultra-high energy cosmic rays. So for this, I want to talk about how neutrinos can help in understanding the redshift evolution of ultra-high energy cosmic ray sources, and for doing that, we have to move to ultra-high energies for cosmic rays, which means above, let's say, 10 to the 17 or 10 to the 18 eV, that I'm reporting here in this plot. And one can try to model the uniform distribution of sources in the universe of, let's say, proton cosmic rays, just to make the model very simple, which emit all identical spectra, so power law with some maximum energy, and with the distribution of sources which can be modeled as a function of the redshift with the power of with this power. So while for cosmic rays, the effect of the difference in this power of m is not relevant, and this is due to the typical interaction length of the processes that we are talking about, which is in this case in which are just taking into account protons, it is just the photopion production with the highest energies, which has a very small interaction length. Actually, for neutrinos, the effect of the different values of m is quite large in terms of the expected flux. In fact, this is in red the expectation that one would have for a pure proton scenario for a source evolution m equals 0 and then increasing to m equals 5 in the blue one. So what has been done by IceCube recently, but also in this Auger paper and other papers in the last years, one can actually scan the source evolution and the proton fraction, and this is actually what should be done because we have the evidence that ultra-energy cosmic rays are not pure protons, so we cannot take into account just a pure proton composition from the very beginning. So we model the distribution of sources as I anticipated before. Then we scan, we scan over the source evolution and the proton fraction. So basically, how much this flux is saturating the total, the whole particle flux. And this gives an exclusion plot in these two quantities, the proton fraction on the y-axis and the source evolution parameter on the x-axis. So in this case, with the non-observation of neutrinos from ice cube above a certain energy, we can constrain the proton fraction to be, for instance, less than 70% with 90% confidence level if the cosmological evolution is comparable to the star formation rate. Now, this is done with some kind of simplistic approach, and we could try to include, for instance, what is the KM3 net highest energy neutrino event detected, and then shape the proton component of cosmic rays from the results that we have on the cosmic ray spectrum and composition. And this is what has been done in our work, in which we, so these gray dots are the points of the ultra energy cosmic ray spectrum, the whole particle, while the orange ones, this is the whole particle rescaled to the proton fraction that we can get with a template fit from the Auger data. And then we can reproduce this part of the spectrum with some combination of source parameters. Here we are interested in highlight what is the different source evolution that we are using, which is not really visible what we do here in this energy region. By the way, the energy of the KM3 net neutrino would correspond, if that is what has been measured, like to 220 PeV, to a proton which has more or less exactly the energy of the ankle, which is the change of slope at 10 to 18.7 eV, which has been measured in the cosmic ray spectrum. Now, if we then on the other side look at the neutrinos which correspond to these scenarios, we find, as I've been showing before, these three lines from red to green to blue, which correspond to increasing the source evolution. In particular, the dashed lines correspond to the interaction of protons of the CMB, while the total, it is both the CMB and the EBL, and in this case, since the energies of the protons are low, let's say, in this configuration, we see that mostly the protons interact, so from the neutrinos, we can say that the protons interact mostly on the EBL. So what one can see here, if we put here also this cross, which correspond to the KM3 net neutrino, is that a source evolution corresponding to m equals 3 of the low energy population can account for this flux. Now we want to do the same at the highest energies, in which we, and here we speculate, this is just an attempt to see what would be an additional proton component at the highest energy, so matching 10% of the whole particle spectrum at approximately 3 times 10 to the 19 eV. And then we want to see what is the corresponding cosmogenic neutrino flux. And here we see first that in this case, the lines corresponding to the CMB and the total are almost the same, because the energy is much larger, so neutrinos are produced with the low energy photon field, which is the CMB. And even in this case, we get to see that the KM3 net flux is reached thanks to a source evolution which is similar to what was before. So what was in the case of the low energy component of the flux. Then now I want to introduce instead also the use of diffuse gamma rays. And then even in this case, I will do it, we did it with the separation for the two different populations, like the cosmic ray protons below the ankle. And in this case, this has been done, the computation of the cascade photons has been done as in this paper by Berezzinski. And in this case, we see, we also show the separated contributions of the photons which come from pair production, which are the dotted lines, and the photons which come from photopion production, which are the dashed. So the bulk of the flux is basically due to the pair production, which is due to the fact that the spectral index which we have used to model the low energy proton population is quite soft. And here it is visible that strong source evolutions are disfavored by Fermi data, which is not actually what we see if we do the same for the cosmic ray protons above the anchor. So in this case, there are two different results with respect to the one on the left. We see that the variations among the different contributions are smaller, and then also that the strong source evolution is allowed. So this is just to confirm or to stress again that a multi-messenger approach, which takes into account all three messengers, which are the protons in the cosmic ray flux, the neutrinos, as well as the diffuse gamma rays, can help in this case, for instance, could help in discriminating if the KM3 net neutrino comes from a low energy population of protons or from a highest energy population of protons. I also want to say something about possible constraints on sources from studies on diffuse fluxes, which was actually connected to what I've been saying before. So from diffuse fluxes, of course, we can constrain the quantity, which is the multiplication by the density of sources and the luminosity in some kind of Hillas plot. So this is the density and the luminosity. But then I also want to show a possible joint source propagation model, which takes into account what is the modeling in the sources, which was what I've been talking about in the previous part of the talk, and the propagation in the extragalactic space. So in this work, the authors have been reproducing the spectrum, the composition of ultra-energy cosmic rays, as well as they give some kind of interpretation of the neutrinos by taking into account population of sources which are allowed from the Fermi limits. So, and thanks to the source density as a function of redshift, they can show that the ultra-energy cosmic ray spectrum can be powered by low luminosity BLX. So, as one would expect, the ultra-energy cosmic ray spectrum is easily reproducible with those sources which have high density at low redshifts. And this is because cosmic rays lose energy, and then they have to do something with the close-by sources, while neutrinos are instead produced mostly in those sources which are very intense, like flat spectrum radio quasars, which instead for the cosmic rays give just a smaller amount of contribution. And then in general, that astrophysical neutrinos can outshine the overall flux of cosmogenic neutrinos, which is actually here. So with this, I am concluding this second part on the ultra high energy topic. And then I want to go to the summary directly, in which I'm just very briefly summarizing what I've been talking about until now. So I've been starting from the existence of astrophysical neutrinos, which has been firmly established in the last decade or even a bit more, from the first evidence of IceCube. And I've been talking about mostly two topics, which is the astrophysical sources that have been found in spatial or temporal association with high energy neutrino events. And then I want to highlight that thanks to source modeling, it is now possible to investigate not just the type of sources producing those neutrinos, but also the site in the source environment in which they could be produced. And then I also want to highlight what I've reported in the second part of the talk, that thanks to multi-messenger approaches, it is or it will be possible to constrain the characteristics of ultra-energy cosmic rays, such as the fraction of protons in their flux and the redshift evolution of the sources, from the observation or even from the non-observation of extremely high energy events. This will be possible thanks also to future, so not just to modeling, but also and even more to future and complementary detection techniques, which will drive our community to the next goal, which could be even more detections of ultra-high energy neutrinos. So thank you very much.
So thanks a lot for being very perfect in time and nevertheless give a comprehensive, complete overview on this very interesting topic. So we have time for questions. Several people join me to congratulate you for the talk. But this is created a bit too. Okay, so if there is any question, you can open the mic or just raise your hand directly. So if not, I would thank you again, Denise, and I would give you the appointment for in 1 month for the next event of this EuCAPT colloquium, and thank you very much for attending. Thanks a lot. Bye.
Thank you. Ciao.